Let's get a screenshot of that. All right, so there's our braking distance formula. Okay, so let's see, part B, we're talking about slope. Part D, they say let V equal 72 miles per hour. Column represents the simplified version. All right, so let me see, what do we got? We got G is 0.2. Let me just gather all the information. That. And then V is 72 miles per hour. So then from there, we got to build an equation. All right, what else am I missing here? So again, we're trying to take a look at, in this case, the relationship of the friction coefficient on the braking distance. So we're trying to isolate F here and D. So anybody remember what little g was?
Gravity?
That is gravity, yeah. It's the force due to gravity in feet per second, and 32.2, does that sound right, the number they gave us earlier? Did they get their worksheet in front of them? 32.2, yeah. All right, so then we also have that little g is 32.2. Let's see, what else do I need? Is this V right here, the 72 miles per hour? Not quite, what's wrong with it? It needs to be in feet per second, yeah. So in order to use this for V, we got to convert that. And again, that's 72 miles per 1 hour. And to convert that to feet, we got to get rid of miles. So 1 mile, remember conversion factors? We did this yesterday, 280. That changes to, what am I doing? Feet. So miles is gone. And then I got to get rid of hours. And I happen to remember that 1 hour is 60 times 60 or 3,600 seconds. So this is the conversion factor we were using the other day to get rid of hours. So we got to take the 72, multiply by 5,280, divide by 3,600. And that is the number we want for V. Anybody have a calculator? Check that out for me. Who's quickest with their calculator? This calculation here, 72 times 5,280 divided by 3,600. Aaron, you got it? 105.6. Okay, we get 2 at that. So 105.6. And that's the feet per second that we need for the formula. All right, so plugging stuff in here, we get D equals 105.6 squared divided by 2 times 32.2, little g, times F we're leaving as our variable, plus G is 0.02. And so we just need to clean that sucker up a little bit. How much they want us to clean it up? Back here, they gave these right here. So I'm guessing this one's the right one right there. Can't be a plus outside the fraction. And we got to have a parentheses around the F plus 0.02. But here it could have been distributed, that 62.4 could have been distributed through. So double checking that. Clean this up. Anybody double check what's 105.6 squared? 11,000 something? 11,000, keep going. 151.36. Okay. And then in the bottom, that's going to be 2 times 32.2 will be that 64.4. And if I distribute that through, remember we did that distributive property a while back? I distribute that 64.4 through there, then it looks like I'll get my formula. Let me condense this so I can fit it. So I think that D is equal to 11,151.36. Did I get that right, Colt? Okay. And then the bottom, I'll have 64.4 times F plus whatever 1.288. All right, so that's our formula that we're applying to the next part of this problem. So let me copy that to the next screen. So I need that to answer question 3. All right, so now for question 3. How do I get to it? Right there. Okay, so now we want to create a table where we're plugging in these different friction coefficients and seeing what happens to the stopping distance in feet, assuming that we're moving at 72 miles per hour, right? So that's important, and there's a slight slope going on here. So none of these went right, or?
I just did.
You just tried the first part? Okay. So I'm going to whip out a spreadsheet to move this along a little quicker. So I'm going to copy that to a Google Sheet. Otherwise, it's painfully slow. So let's see, I'll put that right there. All right, so my formula, I'm just going to list that again. I got D equals 1115. Everybody write that sucker down. 1.36 divided by parentheses 64.4 times whatever F is plus 1.288. Thank you. All right, so that's the formula we're going to apply. So I just need to keep typing that in here. So equals 11151.36 divided by parentheses 64.4 times, again, a spreadsheet's a pretty efficient way to do this. I would recommend trying it. Otherwise, you got to just type this over and over in your calculator. All right, I think I typed it right. Once I type it in once, I can just clean it up and fill it down. I'm not sure how many decimal places they want. All right, so, oops, what happened there? Ooh, I lost my spreadsheet. Oh, there it goes. Got too many screens open, maybe? Computer's not happy about it. So if I try to type those in here, 541.12, 333, 240, 188.21, and maybe I'll do that 0.5 there. All right, so what's happening is the friction coefficient increases. What's happening to the stopping distance? It decreases, right? So what do you think a 0.3 friction coefficient might be? Would that be like an icy road or a dry road? Yeah, it'd probably be an icy road, whereas the 0.9, that's probably more of a dry road. And then we get 181, less stopping distance. So the friction coefficient's a big deal. Could have something to do with the tires too, and the temperature, like Robert mentioned the other day. All right, so 4 values of F correspond to the friction coefficient for 4 road conditions: an icy road, a very good road with great tires, an asphalt road with fair tires, and a wet road with fair tires. So we just need to match which coefficient goes with which. So I'm going to go with what Colt said, that the 0.3 is probably the icy road. Which one's probably the very good road with great tires? 0.9, yeah, that's going to be the best conditions possible, highest friction coefficient. Asphalt road with fair tires, 0.7, I'd agree with that too. And then the wet road with fair tires, 0.5. All right. In the table, the coefficient of friction is increasing at a constant rate since each value went up by 0.2. So, yep, up by 0.2, 0.2, 0.2. Okay. How is D changing as F increases? The stopping distance is decreasing, it's constant, or it's increasing? It's decreasing. Yeah, it's definitely dropping here as that friction coefficient changes by 0.2 each time. Do you think it's decreasing in a straight line, or is it curving down? Yeah, it's curving. And it's hard to tell by looking at a table. You got to look at a graph to see that or start calculating differences. All right, so let's submit that sucker, and we did good. All right, so maybe it was a calculator issue. It said these numbers are the problem right there? Yeah, okay, it's probably a calculator issue. Do you think you used the right formula? Yeah. Okay, so it's just, yeah, so maybe you typed something into the calculator wrong in parentheses or something. Okay.
So you just got like a way there.
Okay. Yeah, maybe it was the parentheses were off. It'd be hard to say without seeing you type it. Jenna, what was next? 5 or 6. So 5, we got Newton's law of gravitation. Oh, that's a great one. Love this problem. All right, so the size of the numbers in this question makes them hard to work with. We got to review back to scientific notation from, man, that was months ago, October-ish. And so we want to restate those numbers in scientific notation first. All right, so let me copy this in my chart. Go from there. So here's our initial information. So here, I think it's just careful counting all those zeros. So what do we got? The mass of the moon. Let me just make sure I'm reading the question right. Use scientific notation, the distance between the Earth and the moon. Let's see. The Earth and the moon are about, oh, that one's easy. Okay. So actually, I better put that on my sheet. With scientific notation, where do we want the decimal point to be for this number right here? Yeah, there should be only one digit to the left of the decimal point. So it's got to be written as 3.84 times 10 to some power. Now, since that's a big number, it's going to be a positive power. And I just have to count how many times the decimal place got moved. So 1, 2, 3, 4, 5. To be 10 to the 5th power. And most calculators, if you type that in, it'll give you back the number you started with, just to double check. So 3.84 times 10 raised to the power 5. And then the mass of the moon. Okay, so that one we're going to have to be a little bit more careful. So mass of the moon is the first one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and then one more for 22. Okay, and it's just careful counting. And it's not a bad idea to get this number on paper and start, counting each one by hand. I thought counting by threes worked for me. Just to double check, there's 1, 2, 3, 4, 5, 6, 7 groups of 3. What's 7 times 3? 21, plus one more place to get the decimal in the right spot there. So 22. Does it want the whole number? Maybe 7.348 times 10 raised to the power 22. And then 1, 2, 3, 4, 5, 6, 7, 8 groups of 3. That would be 24. And then it's going to be in the right spot because that puts me right at that comma right there. So it looks like this one is 5.9722 times 10 raised to the 24th. All right, calculate the gravitational force. Give your answer in scientific notation. Since the number 384 has only 3 significant figures, then we want to round so that the answer has only 3 significant figures. That's 2 decimal places in scientific notation. All right, so we got our formula there. So now we just got to plug into it. So let's see, we've got F is equal to, here it's saying the gravitational constant is that number right there. So I'm going to have the 6.674 times 10 to the negative 11th. Then I got to multiply by one of the masses. So I'll use the moon first, 7.348 times 10 to the 22nd times the other mass, that would be the Earth. Oops. 5.9722 times 10 to the 24th, all over the radius squared. And the radius is going to be 3.84 times 10 to the 5th. And then I have to square that sucker. So now it's just a problem of plugging that carefully into a calculator. So everybody whip out your calculators, try typing that in and see what happens. Let's see if we can agree on a number. Spreadsheet wouldn't be a bad way to do this. I'll type it in a spreadsheet in a minute. That's a 24 at the end there. Sorry, I'm a little messy there. Help. I'm trying to type this into a spreadsheet. Well, tell everybody what you got. See if anyone else got it.
1.98.
What is it?
1.98.
1.98.
It's like this big old.
Oh, it's got times. It's got E something in it.
No.
No, it's just this.
Well, it does have E in it, but it's like.
What's that?
1.92 times 10 to the 26th.
So you get times 10 to the 26th power.
I got 20.
Alana, what'd you
I
get?
don't know.
Did you try typing it in?
Yeah.
Okay.
That was 1.9862195114 e to the 26.
Yeah. So E means times 10 to the 26th power. So it sounds like that's what you got. Okay, so you and Jenny got the same number. So you guys, are you have the same delusion, or you're doing great? Good point. So okay. Give me 1 second. I'll show you what I'm doing here. Oops. Times 10 raised to the fifth. Ah. Okay, so what I'm doing off on the side here is I'm typing that information into a spreadsheet. And since I'm doing scientific notation, I have to do equals first to say, hey, make this calculation for me. Otherwise, it'll just treat it as something else. Okay, so there's all my different constants, right? And this one, when I first typed it in, because of the amount of decimals I was showing, it said, hey, that's 0 pretty much. But if you look and see what I typed, I did that 6.674 times 10 to the negative 11th power. And I just needed to show them enough decimals so I could see the whole number. All right, so the force, help me out here, is equal to, I just multiply the first 3, right? Equals this number times this number times this number. And then what do? Divide by the radius or the radius squared? Radius squared. So once I get them typed into the spreadsheet, it's not so bad to just kind of point and click and fill out the formula. So again, power of a spreadsheet. It's a super powerful calculator. And I get Google saying what Robert and Jenna said, 1.986-ish. E to the positive 26, that means times 10 to the 26th power. So that E is scientific notation on a computer. So that means exactly the same thing as times 10. So that would be about 986 times 10 raised to the power of 26 is what we're coming up with there. So the E is the calculator version of times 10 to the power. Don't confuse it with that magic number little e we talked about the other day. Different idea. That was an awesome one. I'm glad you guys asked about that. So this is what? Homework 4, 5. All right, let's see if I can get a reasonable response. Okay, oh, and then it says only use 2 decimal places. Okay, and that's the idea. Have we talked about significant figures in here? I think we might have way back in week 1 or 2. Probably should talk about those again. Yeah, I think I will. All right, let me just type this in. So let me see, it was 1.962. So 1.96 would be 2 places, is that right? Oh, no, it's 986, right? So 1.99 would be 2 decimal places times 10 to the power 26. All right. Oh, I typed something wrong. What? 3.84. Oh, check it out. What's it asking for here? Trick question. What does it give it to me in? Okay, so how many meters in a kilometer? What does kilo mean? Not 100, 1,000. It means 1,000, yeah. So I could take that phrase right there. So let me do that on a new page. Screenshot. Go. So kilo literally means 1,000. So I can translate this as 3, 8, 4, 1, 2, 3. Kilo means 1, 2, 3 zeros, and then that would be meters. So altogether that would be 384, 1, 2, 3, 4, 5, 6, because I have another 3 zeros there in meters. I want the decimal point to be there. What power of 10 should that be for meters? 2, 3, 4, 5, 6, 7, 8, yep. The 8th power. That fine print gets me every time. Otherwise, ooh, I didn't like that one. Oh shit, oh dear, okay. Guess what we did wrong? What's that? Anybody know what we did wrong? It stems back to this part right here.
They want it in newtons.
They want it in newtons, yeah. And it says the two objects have to be r meters apart. What number did we plug in? We plugged in kilometers. Okay, so problem is, again, none of us got that fine print. Back here, we typed in this number incorrectly, because that would be the measurement in kilometers. How do I change it to meters? What's that? Yeah, to multiply by 1,000. So that 5 should really be an 8 right there, is the problem. So the cool thing about the spreadsheet version of the calculation I just tried to do is all I have to do up here is fix that by raising that to the power 8 instead, and then it updates my answer. So that says, oh, okay, it should just be to the 20th power for the times 10. But otherwise, everything else is all right. Details. Sometimes they're important. Woohoo, you got it right. All right. I got another problem for y'all. Let's see. So here is my work from page 2 the other day. And I'm using the revised formula up here where we threw in the constants for the road conditions that we were given initially. And I've got velocity in feet per second per braking distance right here. So this formula right here allows me to say, given a particular velocity, what's the braking distance? Okay. So what I want to try and do is go the other way, see if I can figure it out. So for example, here I have braking distance from about 4 feet. We got 250 feet here. I'm kind of wondering, what would the speed be of the vehicle if the braking distance had been 200 feet? Why might something like that be useful, given the braking distance, calculating the speed?
Well, if you were a cop.
Yeah, if you were a cop in an accident, yeah, you measure the skid. So I was in an accident once, and the woman who hit me claimed I hit her, right? But pretty clearly the damage was on the front of her car and the back of mine. And the other thing was I claimed she was speeding. She said she wasn't. So what could they do to measure that? Well, they could measure her skid. So let's suppose she had a 200-foot skid in a residential area. Okay. Maybe that's a little bit long. Yeah. Let's go with a 70-foot skid in a residential area. Let's see what that looks like.
That's pretty long.
That's still pretty long, yeah. We'll do that anyway, though.
300 miles an hour.
Let's take a look. All right, so here's what we got. So we're going to go with the conditions we had in that problem over there, which the braking distance was the velocity in feet per second.
What do you need to know, though? I mean, there's a way to just do it like that, but don't you need to know the weight of the car and different things to figure that out appropriately? There's different weight vehicles, different top and different rate.
Yeah, the weight of the car is going to definitely affect it too. Yeah. Yeah, and they have these books, forensic books about how to figure that out with different kinds of vehicles, different slope roads, different conditions. They check out the tires. I mean, if it's really important, they go through quite a bit to do that. Let's see, what was it? 54.74. So I want to find out what would the velocity have been if the vehicle had skidded for 70 feet. So we've solved lots of different kinds of equations in this class. We're going to give this one a shot today. What's the first thing I should do to get that V alone there? What's that? Multiply, yeah. Not square. Square root's going to come up next to get rid of the square. But again, solving an equation, you get the things furthest away from the variable first. If I knew the variable, I would square it and then divide. So that means to solve it, I have to get rid of the division first. So Emily's right. We're going to multiply both sides by 54.74. So that's going to give me V squared equals 70 times 54.74. All right, Colt, what do you want to do next? Yeah, the opposite of taking a square is a square root. So I'm going to write square root on both sides. And the key here is that the square root and the square cancel each other out. So what I should have left here is that v equals whatever that is. So now I whip out my calculator. So everybody whip out your calculators, see if we can agree on the value of that right there. Oops, that's supposed to say 7.4, not 4.4. I'm getting 61.9. Okay, now that's feet per second. We need to change that to miles per hour to come up with an answer for this. So let me put that in my notes. So I'm getting approximately 61.9 feet per second. All right, so what was the fraction we used to convert miles per hour to feet per second? Anybody remember? Yeah, divided by 3,600 seconds in an hour. So we just flipped that here. So to convert this, to get rid of seconds, we make a note that there are 3,600 seconds in an hour and that there are 5,280 feet in a mile. And this will change us to miles per hour. Let's work yet. Times 3,600, still not working. 600 over 5280. And I get 42 miles per hour. .2 maybe. 42.2. Is that a common speed in a residential area? Usually max is like 30 miles per hour. Typically it's more like 25 miles per hour. So this person would have been speeding if they had a 70-foot skid in a residential area. Okay, so this brings us to our next unit, which is on roots. And roots are the opposite of powers. So I'm just going to give you an overview and then I'll set you to work on it. So for example, we know that 2 squared is equal to 4. And so that tells us that the square root of 4 is equal to 2. When we use this symbol right here, this is known as the principal square root. But it turns out most numbers have 2 different square roots. A square root is a number you multiply by itself to get a given number. Okay, so just a note, the square root of 4 asks the question, what number can we multiply by itself to get 4? And certainly 2 answers that question. Is there another number that answers that question? Yeah. Turns out we can take -2 and multiply it by itself, -2, and that gives us 4. So -2 is another square root of 4. Okay. So in general, numbers have 2 roots. So most numbers, oops, it's supposed to be an n, have 2 square roots. One of them is called the principal square root. And the principal square root is always non-negative. And some numbers have another square root, which has no better name than the other square root. Doesn't get a special name. And that one is usually negative. Okay. So for example, 4 has square roots of 2 and negative 2. 9 has square roots of what? 3 and negative 3. Okay. Can you think of a number that doesn't have 2 square roots? Yeah, it's 0 and negative 0, but negative 0 is the same thing as 0. Yeah. So 0 is the exception. So 0 has only one root. Oops, 0. Right, and that's itself. Square root of 0 is 0. So usually when we're solving an equation, like if somebody says, hey, I squared this number, it's equal to 4, then the answer is either the square root of 4, which is 2, or the opposite of the square root of 4. Order of operations here is to take the square root first and then take its opposite. Right? So there's a symbol for the regular square root, and then you just throw a negative sign in front for the other. Sometimes you see people condense this and say x is equal to plus or minus the square root of 4, which would mean x equals plus or minus 2. Have you guys seen that notation before with the plus and minus thrown together? Yeah. So it's nice because it's just kind of shorthand, but that's shorthand for x equals 2 or negative 2. Okay, so it's just a shorthand. And it's just there to remind us that most numbers have more than one square root. They have 2 square roots. All right, so that's square roots. There are other kind of roots, though. So if I can take a number and cube it, for example, 2 cubed is 8, then there's got to be a cube root. And the way we write that is we start with the square root symbol, but we put a little 3 inside that hook right there to indicate we're looking for a number that was written down 3 times and then multiplied. So what's the cube root of 8 have to be? 2. Now, unlike square roots, cube roots don't have multiple options. And here's why. If you take negative 2 and you raise it to the 3rd power, that's going to give you negative 2 times negative 2 times negative 2. What's a negative times a negative? Positive. But now I have that positive times a negative, and the answer ends up being negative. Yeah. So when you cube a negative, you get a negative. So you only get one option for the answer. But with squares, when you square a positive or a negative, you get the same answer. You lose track of the sign. Okay, so squares are a problem. That's where that plus and minus comes up. Cubes, they ain't no problem. They're actually easier than squares in the sense of trying to reverse them. Okay. So tell me then, what is the cube root of negative 8? What number do you multiply out 3 times and get 8? Or negative 8, excuse me. It'd be negative 2. Since I start with a negative in there, I get a negative back. Yeah, so cubes hang on to negatives. Squares don't. Okay. How about 4th powers? So consider negative 2 to the 4th power versus 2 to the 4th power. Let's do the easier one first. That's just 2 times 2 times 2 times 2. Well, 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16. When I do the negative version, negative 2 times negative 2, and then I have another negative 2 times negative 2. These guys give me a 4. Those guys give me another 4. 4 times 4 is still 16. So notice fourth roots have the same problem as square roots. Yeah, if it's an even power, it kills the sign, is what happens, yeah. So same problem as squares. And so we'll just summarize it right up. Emily cut right to the chase. Even powers eliminate squares, or eliminate negatives, excuse me. Which makes undoing them a problem because they got rid of the negative. You don't know whether the answer was positive or negative when you try to undo it. Okay, so even powers are actually trouble because of this right here. So if I said, hey, I had some number and I raised it to the 4th power and I got 81. What number was it? Well, one way to solve this would be by taking a 4th root. So like a square root gets rid of a square, a 4th root would get rid of that. So if I take x to the 4th equals 81, then I could take the 4th root of each side. So then x here should be equal to whatever the 4th root of 81 is. I heard somebody whisper it. 3, it turns out, is what that is. Some calculators have a 4th root button, some don't. Does anybody know a trick to dealing with that? Yeah, so if your calculator has something like a y root, then you can do a 4th root with that. Usually the way they work is you would type the number you want the root of first, then you type the symbol, then you type the number in question, and it should spit out the answer, is the way it works. So that on most calculators will give me 3. Another trick to doing that, the 4th root is the same thing as a power of 1/4. So on a calculator, I could type 81 raised to the power parentheses 1/4. So try that on your calculator right now. See if you can get that to work out as a 3. I'm going to try it on my Google calculator. 81 raised, oops, to the parentheses 1/4. So the 4th power is the 4th power. The 1/4 power is the 4th root. That's the way that's interpreted. And Google says, yep, it's 3. So again, I'm just bringing this up because we're going to need ways to check this on our calculator. Now here's the problem with me solving this equation right here. What did the 4th power lose track of?
Negatives.
Yeah, I don't know if that was +3 or -3. It could have been either. So I still have to say, it could have been plus or minus because it's an even power. So because of the even power, we need that plus or minus. Okay, so that's an overview of roots. If you haven't already taken a look at the prep for 4-6, please do so soon. Otherwise, for homework, clean up whatever you need to clean up, and please start on this worksheet for homework, and then we'll go over it together on Monday. We have one more lesson to get through, and then we have to review for the final. Last week of classes is next week. Yeah, almost done. Congratulations.